Hello, in this lecture I will explain what is mathematical induction. Mathematical induction is a logical method to prove that a statement, a claim or an equation is true for all the natural numbers. A natural number is an integer that is also a positive integer, like 1, 2, 3, 4, 5, 6, etc. And when you want to prove that something is true for all the natural numbers by mathematical induction, you will have to perform two stages. In the first stage, actually you will check the statement for n that equals to 1, and if the statement is indeed true for n that equals to 1, then we will go to the second stage. That is to say, we will assume that the statement is true for n, and then we will prove that the statement is also true for n plus 1 according to our assumption, or we will rely on our assumption that it is true for n plus 1. When we want to prove it for n plus 1, we will rely on our assumption that it is true for n. Okay, and actually in this way, by doing those two stages, we actually proved that the statement is true for all natural numbers. And I will explain why. Because in the first stage we proved that the statement is true for n that equals to 1. And in the second stage we proved in general that if it is true for n, it also must be true for n plus 1. So we can say that we are sure that it is true for n that equals to 1. And from our general proof that if it is true for n that equals to 1, if it is true for n, it must be also true for n plus 1, we can say that because of the fact that we know for sure that it is true for n that equals to 1, so it must be also true for n plus 1, for 1 plus 1. That is to say, it must be true for 2. Okay? And then we will repeat on the same process. Now that we know that the statement is true for n that equals for 2, we can rely on our general proof in order to prove that it is also true for n plus 1. That is to say, it is also true for 2 plus 1. That is to say, it is true for 3. And as we know that it is true for n that equals to 3, we again will rely on our general proof that if it is true for n, it must be also true for n plus 1. We will rely on it in order to prove that it is also true for n that equals to 3 plus 1. That is to say, So now we know that it is true for 4. And then we repeat on the same process again and again in order to prove that it is true for n that equals to 5 and 6 and 7 and so on and so on. So in this way we actually proved in these two stages that the statement is true for all the natural numbers. Okay, so in order to clarify the topic, I will give you two examples. We will start with the first example. The first example will be one plus 2 plus 3 plus n equals to n times n plus 1 all divided by 2. So we must prove that this statement 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. We must to prove, okay, we must prove that this statement 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2 for all the natural numbers. So in the first stage we will check that this statement is true for n that equals to 1. Okay, so in this side of the equation we will have 1 because n equals to 1 equals to n times n plus 1. When n equals to 1 it will be 1 times 1 plus 1 all divided by 2 and equals to 1 times 1 plus 1 is 2 all divided by 2. 1 times 2 is 2 all divided by 2 is 1. So 1 is equal to 1. So actually we passed the test and we actually verified that this statement is true for n that equals to 1. Okay, now we will go to the second stage. I will write it in a new page. The second stage is actually, in this stage we will assume that this statement is true for n and then we will prove it for n plus 1. So the statement for n will be 1 plus 2 plus 3 plus n equals to n times n plus 1 all divided by 2. Okay, so this is the statement for n, or this will be the induction hypothesis. Okay, so we assume that this statement is true for n, and so this is the first equation, and then we will have to prove that this statement is also true for n plus 1. So the expression for n plus 1 will be 1 plus 2 plus 3 plus n plus n plus 1. So we will add numbers until n plus 1 because we want to prove that this statement is true for n plus 1. So here, wherever it is written n, we will write n plus 1 because we want to prove the statement for n plus 1. Okay, so instead of n, we will write n plus 1. And in the brackets we have n plus 1, so it will be n plus 1 plus 1. Okay? So, actually, the second equation is the statement that we must prove for n plus 1. The first equation is the induction hypothesis. We assume that equation 1 is true, and as we rely on this assumption, we will prove that this statement is true for n plus 1. That is to say 1 plus 2 plus 3 plus n plus 1 equals to n plus 1 times n plus 1 plus 1 all divided by 2. So we, in this side of the equation, we will add numbers until n plus 1, and in the other side, instead of n, we will write n plus 1 because this expression is for n plus 1. Okay, so in order to prove that the second expression for n plus 1, or the second equation for n plus 1 is true, we actually will rely on our assumption that this statement is true for n. Okay, so if we look at the second equation that we have to prove, we should look on this expression. Actually, this expression in the green color is exactly this expression. They are exactly the same, and this expression equals to this expression, n plus 2 plus n equals to n times n plus 1 divided by 2. So we can say that this expression equals to this expression because of equation 1. They are the same, because this is the same like as this expression, and this equals to this, so this also equals to this. So we can substitute the expression in the green color by n times n plus 1 divided by 2. Okay, so we'll do it now. Instead of 1 plus 2 plus 3 plus n, we will write n times n plus 1 divided by 2 because they are equal to each other. And here in the second equation that we have to prove, is written n plus 1 So we will copy it as it is. All equals to n plus 1 times n plus 1 plus 1. N plus 1 plus 1 is n plus 2, so we will write it. It is n plus 1 times n plus 2. All divided by 2. Okay, so we have to prove that the second equation is true. And in order to prove it, we will divide both sides of the equation by n plus 1. Okay, because we have n plus 1 in both sides of the equation, we can divide by n plus 1 because n plus 1 will never be 0. So we are not dividing it by 0, so it is something that we can do. It is allowable. Okay, so we divide both sides of the equation by n plus 1. And we will get that n times n plus 1 divided by n plus 1 is n, divided by 2 plus n plus 1 divided by n plus 1 is 1, equals to n plus 1 times n plus 2 divided by n plus 1 is n plus 2, and we divide it by 2. So here we have n divided by 2 plus 1 equals to n plus 2 divided by 2. So we can separate n plus 2 to 2 parts. Okay? So after we separated it to 2 parts, we got that n plus 2 divided by 2 is n divided by 2 plus 2 divided by 2 equals to n divided by 2 plus 1, and we know that 2 divided by 2 is 1, so we will write it down. So we got an identity. The left side of the equation equals to the right side of the equation. N divided by 2 plus 1 equals to n divided by 2 plus 1. So actually we proved that if this statement is true for n, it must be true for n plus 1 also. And in this way, actually, we proved that this statement is true for all the natural numbers, because in the first stage we proved that this statement is true for n that equals to 1, and in the second stage we proved that if it is true for n, it must be true also for n plus 1. So we actually proved already that it is true for n that equals to 1. And from our general proof that if it is true for n, it must also be true for n plus 1, we can say that because of the fact that it is true for n that equals to 1, it must be also true for n plus 1, that is to say 1 plus 1, that is 2. So it must be true also for n that equals to 2. And then we will repeat on the same process again, because we know that this statement is true for n that equals to 2. And according to our general proof that if it is true for n, it must be also true for n plus 1, and we know that it is true for n that equals to 2, it must also be true for 2 plus 1. Okay, because it must be true for n plus 1, so it must be true for n that equals to 2 plus 1. That is to say, it must be true for n that equals to 3. And when we know that this statement is true for n that equals to 3, it must be also true for n that equals to 3 plus 1, according to our general proof that if it is true for n, it must also be true for n plus 1, and so on. And this way we will also prove that it is true for 4 and 5 and 6 and so on and so on. So in this way we actually proved that this statement is true for all the natural numbers. Okay, so I will give you another example. The second example, so it is 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 square, all divided by 4. Okay, so this is the example. 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 square divided by 4. So we must prove that this statement is true for all the natural numbers. Okay, in order to prove it, we will start with the first stage. That is to say, we will prove that this statement is true for n that equals to 1. So, in this side of the equation, we will have 1 to the power of 3, because n equals to 1, equals to n squared times n plus 1 square divided by 4 will be 1 square, because n equals to 1, times in the brackets we will have 1 plus 1 square, all divided by 4. So 1 square is 1, and 1 plus 1 is 2. 2 square, all divided by 4. So it is 1 times 1 to the 1 square is 4, divided by 4. 1 times 4 is 4, divided by 4 is 1. So 1 equals to 1. So we passed the first stage successfully, because we actually proved that this statement is true for n that equals to 1. Now we will go to the second stage. So I will write it in the new page. Now we will go to the second stage. That is to say, we will assume that this statement is true for n, and we will prove it for n plus 1. So the inductions hypothesis will be equation 1, that 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared. In brackets we will have n plus 1 square all divided by 4. So the inductions hypothesis will be the first equation, 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 will equals to n squared times n plus 1 square all divided by 4. That is the inductions hypothesis or inductions assumption. So we assume that the statement is true for n, and we will prove it for n plus 1. Now we will create the second equation that will be the expression for n plus 1. 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3. After n we have n plus 1 to the power of 3, because we want to prove that this statement is true for n plus 1. Okay, so we will add numbers, not until n, but until n plus 1, because we want to prove that the expression, that the statement is true for n plus 1. So plus n plus 1 to the power of 3 equals to, here in the original statement we have n squared times n plus 1 square divided by 4. So wherever it's written n, we will write n plus 1, because we want to prove the statement for n plus 1. So it will be n plus 1 square instead of n, we will write n plus 1 squared all divided by 4. Okay, so as I already said, because we want to prove that the expression is true, this statement is true for n plus 1, we created the expression for n plus 1. So in this side of the equation we will have numbers that added until, not until n, but until n plus 1, because we want to prove it for n plus 1. And then in the other side of the equation, wherever it is written n, we will write n plus 1, because we want to prove that the original statement is true for n plus 1. Okay, so wherever it is written n, we will write n plus 1. So we will have n plus 1 square times, instead f we will write n plus 1. So here it is n plus 1, so we write n plus 1 plus 1 squared, and all divided by 4. Okay, so n plus 1 is n plus 2, so we write it down. So the only change from here to here is that I change n plus 1 plus 1 to n plus 2. All other things are the same. So we should look on this expression. This expression is exactly same, is identical to this expression, and this, so they are identical to each other. The expression in the green color are identical to each other, and actually, and we can say also that all three expressions in the green color are identical to each other. Yes, it is 1 plus 2 plus 3 plus and 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3. In these three lines, yes? But we see that in the first equation, this expression actually equals to n squared times n plus 1 squared, all divided by 4. So actually we can substitute this expression by this expression, because they are identical, they are equal to each other. Okay? All these three expressions are equal to each other, and this expression equals to this. So also this expression equals to this, because all the three expressions are identical. So we can substitute this expression by n squared times n plus 1 squared, all divided by 4. So we will do it now. Okay, they are identical, so we substituted one by another. All these expressions in the green colors are identical, and in the second equation we have also plus n plus 1 to the power of 3, so we will copy it as it is. And all equals to n plus 1 square times n plus 2 square, all divided by 4, so we'll copy it as it is. So here we have the second expression that we have to prove, as we rely on the second expression, on the first expression, that is the induction hypothesis. We will prove the second equation for n plus 1. We rely on the first expression, that is the induction hypothesis, that says that actually the original expression is true for n, and as we will rely on this assumption, we will prove that this expression, this statement, is true for n plus 1, that is what is written in the second equation. Okay, so here in the expression that we have to prove, we have n plus 1 square in both sides of the equation, so we will divide both sides of the equation by n plus 1 square. And we actually will get that n square times n plus 1 square divided by n plus 12 square will be n square, and we divide it by 4, plus n plus 1 to the power of 3 divided by n plus 1 square will be n plus 1, all equals to n plus 1 square times n plus 2 square divided by n plus 1 square will be n plus 2 square, and we divide all by 4. So here we can multiply both sides of the equation by 4. Okay, n square divided by 4 times 4 is n square, plus n plus 1 times 4 is 4n plus 1, and n plus 2 squared divided by 4 times 4 will be n plus 2 squared. So here we can actually open the brackets and do the multiplication. N square 4 times n is 4n, 4 times 1 is 4, equals to okay, n plus 2 square is n plus 2 times n plus 2. Again, we will open the brackets in the left side of the equation. N times n is n squared. N times 2 is 2n. 2 times n is 2n. 2 times 2 is 4. N squared plus 4n plus 4 equals to n squared. 2n plus 2n is 4n plus 4. So here the left side of the equation equals to right side of the equation. In both sides we have n squared plus 4n plus 4. So we actually proved that if this statement is true for n, it must also be true for n plus 1. Okay, and in this way we actually proved that this statement is true for all the natural numbers, and I will repeat briefly why it is true for all the natural numbers. Because of the fact that we have already proved that this statement is true for n that equals to 1. Because we checked it that it is true for n that equals to 1, and we actually found out that it is true for n that equals to 1. And then in the second stage we actually proved that if it is true for n, it must be also true for n plus 1. So we can say that because of the fact that it is true for n that equals to 1, and we have already proved in general that if it is true for n, it must be true for n plus 1, we can deduce it that because of the fact that it is true for 1, it must also be true for 1 plus 1, that is n plus 1. Because we proved that actually if it is true for n, it must be true for n plus 1. So if it is true for n that equals to 1, so it must be true for 2. For n that equals to 1 plus 1, that is 2. And when we know that it is equal, that the statement is true for n that equals to 2, it must be true for n that equals to 2 plus 1, because we in general proved that if it is true for n, it must be also true for n plus 1. So it must be true for 2 plus 1, that is 3. And when we know that it's true for 3, it must also be true for 3 plus 1, that is n plus 1, because we have already proved that if it is true for n, it must be true for n plus 1. And we will repeat on the same process in order to prove that it is true for 4 and for 5 and 6, 7, 8 and so on and so on. And actually in this way we proved that this statement is true for all the natural numbers. Okay, so we can summarize the lecture and say that mathematical induction is a logical statement, is a logical method to prove that a statement or equation or a claim is true for all the natural numbers, and the natural number is an integer that is also a positive number, like 1, 2, 3, 4, etc. And we have two stages in the mathematical induction when we want to prove that the statement is true for all the natural numbers. We will have two stages in order to prove it. In the first stage, we will check that the statement is true for n that equals to 1, and in the second stage, we will assume that the statement is true for n, and we will prove that the statement is true for n plus 1. When we rely on our assumption that it is true for n. Okay, so in this way we actually proved that the statement is true for all the natural numbers, because of the fact that we have already proved that it is true for n that equals to 1, and according to our general proof that if it is true for n, it must be true for n plus 1. So we proved that it is true for 1, so it must be true for 2, that is 1 plus 1. And when we already know that it's true for 2, it must be true for 2 plus 1, according to our proof that if it is true for n, it must be true for n plus 1. And when we know that it is true for 2, it must be true for 3 and 4 and 5 and 6. According to our general proof that if it is true for n, it must be true for n plus 1. And in this way we actually proved that the statement is true for all the natural numbers. Okay, thank you very much.